it's a living CAD model right there.
Yeah.
You can have that until manufactured.
So can you just like go to the 3D printing lab and send them that, or like?
I'm not really sure. I can go over there and ask like, hey, how do you go about making this?
Okay.
And he'll connect those in the right direction.
Okay.
But that's easy enough. And then literally for the 2x4, you really just kind of you build that out.
Yes, we got your.
Alright, let's finish.
Scratch paper from the class. Yeah.
This idea came about first like 10 years I told that to so like everyone is actually started. Nice.
You like that.
Okay, so I'm back, and so
we are going to talk about new things. But just to recap a bit, from previous classes, we have seen application of expanded decomposition. There are two main things. One is spanner and cut specifier. This is basically the way to specify a graph, right? And the key thing to get this is to use something called repeated expanded decomposition. Can any one of you remind what is this?
You do expanded decomposition once, then whatever the intercluster edges, we do expanded decomposition on it again. So that
Very good. Yes, right. And once you have done this like log n times, then basically given any graph, you basically get that you can decompose a set of edges of graph into a bunch of expander that are not overlapping too much, because each node will contain in at most log n many expanders. Yeah. And know that when we compute this thing, the phi parameter that we use is actually quite high. It's not like small. It's something like polylog n, right? We just need phi to be small enough so that the number of intercluster edges is half. That's all we need. So we can set phi to be quite big. Yeah. And another thing that we saw is how to get deterministic min cut just by using expanded decomposition based on this expansion and not conductance, right? Here we reduce the number of nodes as well. By the way, I mentioned one thing about like vertex cut specifier. So it turns out that this will be related to something else later in class. So I will just talk about that later. Okay. Okay. So now today, it's gonna be something like quite new and like quite different from the thing that we have seen in class. It is a push-relabel flow algorithm. So this is like a framework for computing, for solving some flow problem. Many things based on flow can be solved using this framework. It's not just one particular algorithm. Originally, it is designed for solving exact MAC flow long time ago. Nice thing about this is also that it seems to be the fastest algorithm for solving MAC flow in practice, actually. So it's nice to at least see it once, actually. Besides push-relabel, there are actually some other framework for solving flow problem. Most likely what you have seen is augmenting path-based algorithm, keep finding augmenting path and get a MAC flow, like a Ford-Fulkerson algorithm, for example. And there are other frameworks, like blocking flow and multiplicative weight update framework. So if you haven't seen this, I actually like taught it in my previous class. So you can have a look if you want to. It's quite nice, and like this thing is quite simple and similar to push-relabel that I'm gonna talk about today. It's just that it turns out that push-relabel is more flexible. It seems to be more powerful to me. Yeah. But this thing is conceptually quite simple and nice. This thing is also very, very nice. So, okay. So why do I talk about push-relabel? It's like a one framework which is like nice in many ways. Like not just that you can solve max flow problem. People use it to solve many other things actually. So the nice thing, if I need to capture in one sentence, is that it allows some kind of amortization. That is, so you don't need to really understand this. I just want to like tell you the story. Yeah. That is like people use it to solve like when you have problem where you need to solve many flow problem like n flow problem, but these problem have some related structure, like some additional structure together. It turns out that you can use push-relabel to solve it, to solve n instead of this problem just by running the algorithm just once. So in this way, it's faster. Yeah. So, and by using this kind of thing, like there are many algorithm based using this amortization trick and get fast algorithm. So that's like a classical, a nice aspect of push-relabel. It turns out that there are a more modern aspect why this is a cool thing. So it turns out that this framework is very nice for finding low conductance cut, to find sparse cut, and this is why it's related to expander thing. So this is a main takeaway thing that I want to tell you in like this class and maybe next class too, and next class too. And what do I mean by powerful? Like it's gonna be fast, like near linear time, and you can make it local. Like you don't need to read the whole graph, and you still do something meaningful. It is also dynamic. So like many nice things about it. And basically, from each of these aspects, you get some new application just from this framework. So the application from being fast is that, and we will see today in this class, is that we can implement the matching player in the cut matching game framework in a linear time. So we used to assume that like we can do it in linear time, like by assuming linear time approximate max flow. But later in class, by the end of this course, what I really want to do is to actually tell you how to implement this thing, like how to get approximate max flow in linear time. So we better not assume it and like and build something without this assumption. Yeah. So, yes.
What do you mean by implementing the matching player? Because previously it seems we have an arbitrary matching player, right? Like we can.
Oh yeah. So what I mean is that think of when you want to find a sparse cut based on cut matching game. So one player is cut player, and another one is like a subroutine that either finds sparse cut or embed a matching. So that subroutine, this is what I mean by matching player. Yeah. And that subroutine, we said before that we can just use approximate max flow, which is fast. But here we're gonna see that it can be done in linear time without any assumption. And there are two other aspects like local and dynamic. This I'm gonna talk next time. So by local, like it can find sparse cut without reading the whole graph. Dynamic, it can use to maintain expander under edge updates. Next class for this thing. Okay. So to talk about push-relabel, I really need to tell you about some terminology and how we think about flow, because it's kind of quite different from the ST flow terminology that you have seen in basic algorithm class. And by the way, this framework will work in directed graph too. Not like it's just work in directed graph, but because most of the application that I want to tell you is on undirected graph. So I will just present a notation based on undirected graph. Yeah. But like once you have seen that something can be done using push-relabel in undirected graph, you should think that it should be extended to directed graph too. Okay, now to talk about push-relabel, the key concept that we will need is something called a preflow. But instead of directly talk about that, I need to build some notation towards it. Okay, so what we will work with is a undirected capacited graph. Okay, capacited graph with capacity C, and each edge has non-negative capacity. This is normal, and given any like set, like given E prime, a set of edges, C of E prime is just the total capacity of E prime. And here I denote the cut size of S. It's just the total capacity of edges, like crossing the cut. Okay. So now flow. The notation of like what I will call flow here is gonna be very flexible, much more flexible than basic algorithm class. Flow is really just a function that map two nodes, two pairs, like a pair of nodes to a real number. And if it satisfies the following, then I call it flow. That is first, it is anti-symmetric. Okay. And second, if there is no edge, like if UV is not an edge in graph, then it should be 0. That is flow. But there is meaning about this, right? The meaning is that if flow from U to V is flow UV is greater than 0, then it just means that there is a mass like of flow. I call it mass too. That is route from U to V in this direction. There is direction, okay? So from U to V. And by the way, and if I look at U to V and this is less than 0, then it just means that the flow actually is routed from V to U in this edge. And now the congestion of the flow is nothing but the ratio, the maximum ratio of the amount of flow over the capacity of edges. And if this is at most 1, then we say that the flow is feasible or it respects the capacity. Okay. And next is that is the net flow going out of U. So if you have U here, and if this is 10, this is 1, and this is 5, then the net flow going out of U is going to be 10 plus 1 minus 5. Okay. So I really just summing over all this. But sum of the term here is going to be negative because the direction, like this term, this one is negative, for example. So this is going to be like 6. And net flow coming into U is really just like the same thing but flip the direction. So it means what? It means that net flow into U is going to be just flip the direction. And I can talk about like net flow going out of the set. Now I just sum over all U. that flow going out of a set S is just F out of S is just summing over F out of U. Okay, and the same for flow into S. Okay. So here you can see that this is true for all the time. And why is this true? Like, why is it the case that flow out of everything is always 0?
For every edge, there are two directions.
Yeah, exactly. For every edge here, you count UV. You count this thing, like when you count at V, this thing gives some negative number, but when you count at U, you just cancel that negative thing by the same amount. So everything just cancel. Okay. So the notion of ST flow from basic class, like basic algorithm class, is just the flow such that for every other node which is not ST, the flow out is 0. Like it's conserved. The flow is conserved at every node which is not S and T. And flow will need to respect the capacity. But here we are much more flexible, right? When I talk about flow, it might not respect capacity, and you might not have like a flow out equal this thing may not be 0 at every node. Okay. Next is the demand function. So if I set a demand, demand function is just it's just a function that assign number on each node to some value, and we set the flow satisfy the demand, dem if flow out at every node is equal to the demand. So for example, if I define demand to be like some number, like demand here is S and T, and this is demand is here is 10, and this is minus 10, and everything else I define it to be 0. Then the flow that satisfies this demand is really just ST flow, right? So it's gonna be the ST flow from basic class algorithm, basic algorithm class, with value val. Make sense? Okay. And okay, and I can also define the total demand on the set to be like summing over demand on the set S. And can you tell me why the demand is satisfiable if the sum of the demand is 0? Okay, maybe too easy. I don't know. So, okay.
It's a homework, these two.
Oh yeah, I see. Right. Yes, it's in the homework, right? Okay, yes. So this also like, so yeah, the demand is satisfiable by a feasible flow also if this is true for every set S. Okay. This is just reminding of the homework. Yeah. Okay, so that makes sense, but actually, so basically the demand function allows you to talk about just when the demand is not just at S and T, but when like you have general demand, like some node have this demand, some node have this minus demand, and so on. It's more general than ST demand. But this is not as flexible as we want, actually. This is why I need a more flexible formulation. Because imagine the following. If you have some some set of node A and set of node B. And I want to say that like I want to find some flow like such that each node in A send some flow of 1 unit flow to some node in B. Okay. So every node in A should send exactly one one unit of flow, but each node in B might receive at most 1 unit of flow. Okay. Here it's not gonna be clear what you should define the demand on vertices of B, right? Because we don't we allow flow to get to any node in B. So like if you want to model this situation, one way to do is that you can just add a super source and super sink and set the capacity here to be 1 and this is 1, and find and check if there is a flow, check if there is ST flow of size A, right? If there is, then you're gonna get this kind of flow where every node in A will send some unit of flow to some node in B, and each node in B can receive at most 1. So you can model this situation by adding S and T as a super source and sink. But actually, like I really don't want to work with this kind of thing. Like I don't want to, like I really want to work on original graph. Yeah. So to really work with original graph, I need to define the following, like a source function and sink function in this way. So here a source function is just a function that maps each node to non-negative number, and the same for sink function. Okay, and you think of each, like the source on V is specify the amount of mass or flow that initially is placed on a node V. Okay. And sink function is like a capacity of V as a sink. So imagine like if I say that this thing is 10, then think like you have 10 unit of flow, 10 unit of mass here, and if this thing is 5, then it's like this thing has 5 unit of sink capacity, and you kind of would like to move each of the mass somehow to some sink. That's how you should think about this formulation. And like you would like to move all of this to some sink, but this guy can absorb like 5 unit of flow of mass at most. Okay. So now I'm gonna define more things. We can define this flow at V. Flow at V is the initial mass at V plus the total flow into V. So this is the net flow ending at V after routing F. Okay. This is just the definition, but it makes sense, right? Like, so like after you route F, you ask how many mass that remains at V. Yeah. Okay. And I can define like total source of the set S and total sink of the set S2. Okay. And now here is the definition that will make sense because, okay, the definition is this. I will say that F satisfies the source sink function if F out, like the total flow out of V, is at most source at V. That is, the net flow out of V is at most its initial mass. You cannot send something out more than what you have from the beginning. Okay. And another thing is that the flow that ends at V cannot exceed the sink at V. So, okay. And actually, like, any question about the definition first? Like, so there are like a lot of terminology. Does it like still make sense intuitively?
In F at V, why aren't you subtracting F out V as well from the, like, it makes intuitively sense, right? You're subtracting the flow going out of V.
So note that F in already like it already subtract the out already.
Yes.
Like I already define it to be this thing, right? At V is summing over W into V. So if this is V and this is W that go out of V, then this H already contribute negative to F in. Yeah. Okay.
So is this following the old, it's not following the old rule that F WV has to be equal to minus F VW.
Oh, we still have this, that FWV is equal to minus VW. We always have this.
The first condition is just F at is at least 0.
Exactly. Like this thing is the same as saying that F at B is at least 0. So you can succinctly say this, that is, we want that F at V is between TV and at most 0. This is what it means by a flow satisfied source sink function. So it's like after you flow F, the amount of flow that end at each node is not negative, and it doesn't exceed the sink capacity at each node. Okay, so can you just spend a bit of time to do this, like to really familiar yourself with this notion? Suppose that you are given some demand function, demand, and you can actually define a source sink function that captures the demand in the following sense. That is, if can you try to define sourcing function that capture the demand in such a way that if like F satisfy this thing if and only if F satisfy the demand. How would you define sourcing function? it's gonna be something that just makes sense. It actually, and you can try to guess too. Can you? Anyone?
Whenever it's positive demand, you make the like the mass function, like what's like delta V, like demand of V. Otherwise, you make like TV equal to minus demand.
Exactly. So, like when you have the demand, like there are like a bunch of guys that have plus a demand, positive demand, and a bunch of guys that have negative demand. And you can think of this thing as a source, and this thing as a sink. Right? You want to send the thing from plus thing to the minus thing. So you just really define the source function to equal the demand whenever it is positive, and everything that is like otherwise it's just zero. And the sink is just you define it to be like whenever the demand is negative, you define it to be like negative of that. Okay. So this is again positive thing. Okay.
We can write it as like the maximum demand V and 0. The delta V equals maximum demand V and 0. And the sink function is the minimum of 0 and the demand V.
Yeah. Yes. Right, exactly. Yeah. Max 0 demand V and min 0. Is it? No, max. It should be max, I think. Yeah. Okay. So it will make sense, and this is going to be true that given any demand, you can define sourcing functions such that f satisfy this demand if and only if f satisfy this sourcing function. And there is a proof, but it's boring, and I will just skip it. But like maybe it's good to really like, and if you know like a much better proof, please tell me, because I have this only clumsy proof here, which is long. But yeah, okay. And this thing gonna be true as well, like the analog thing that I say, like what kind of demand is satisfied by any flow, what kind of demand satisfied by any feasible flow. Here you're gonna have that sourcing function is satisfied by any flow at all if the total source is at most a total sink. That makes sense. Like you cannot like
Generate.
Yeah, if you have a source which is more than sink, then you're not gonna absorb all of them. Yeah. But as long as this is less than this, then there is a flow at least that send the source to sink. Yeah. And if you want source sink function to be satisfied by some feasible flow, then here you need that for every set, the total source, like the total source in S, after you minus the sink function, the total sink in S, like this is less than the size of the cut. And this also makes sense because if this thing is more than the size of the cut, then there is no way. Like this thing is like the amount of mass that will remain even if you absorb all of the mass inside the set. And this thing needs to be sent out of the set somehow. And if this is more than the cut size, there's no way to get a feasible flow. You cannot respect the capacity. Okay. And to make this formal, you can use max flow min cut again. Okay, so with now we have source sink function. We like, and this is the way you should, and I actually think about flow. Like, there are some node with initial mass, and some node with like some sink capacity, and you want to send mass to sink. Yeah.
In the first, the first statement, delta of v is less than or equal to T of v. There we are not satisfying some of the sink, right?
Say it again.
So when delta of v is less than or equal to T of v,
Yeah.
then we are not satisfying some of the sink rate.
Yeah, but here we really just like, we don't need to certify, like we don't need to saturate the sink.
Okay.
Yeah, we just need to send flow to a sink, and it's fine to not saturate the sink.
But we should
This is like the goal of giving this formulation, because we don't need to saturate exactly each sink. I allow like just putting some mass as long as it not exceeds the sink capacity.
And delta of v need to be saturated always. The source need to saturate always.
Yeah, the source need to be sent. Like all the mass, all the initial mass at each node need to be absorbed at some sink. Like this is like, it's asymmetry here. Like, yeah. More question about intuition also? Yes.
So the sink function of the source need to be 0 or the
Oh, they can be, both of them can be positive. Like if this node, let's say, have a source like 10, and if it has sink 5, then you can just say that, okay, from the beginning, make 5 of them absorb here. So, and if the sink is like 15, then you really don't need to do much about this node. Just move all the source to the sink at the same node. Yeah. All right. Now preflow. So preflow is this. Given the sourcing function, a preflow is just, with respect to this, is just the flow such that this condition is still true. That is, f at v is still at least 0 for all v. But now we allow that the flow at v can still exceed the sink capacity. Okay. So intuitively, it means this: like, if this happens, then some unit of flow at v, it still doesn't reach sink yet. There is still some unit that remains at v, and so it's like we are not finished sending flow yet. That's why we call it preflow. Okay. And then I would need more definition just to talk about things, but all of this is gonna be just the word to talk about things that make sense. And so here I define absorb mass at v. It's really just amount of flow. Like it defined to be the minimum of flow at v and sink at v. So, but it's really just the way you think about how much mass is absorbed at v. Like, so if this is v and you can absorb at most t of v. So if you have this many mass, like 5 out of 10, then the absorb at V is 5. But if your mass is like now like 20, you still absorb like 10 out of 20. Okay.
T of V equals 10 here, is it?
T of V is 10 here. Yeah. Okay. Okay. So you keep absorbing the mass until it reaches the capacity. So absorb at V is minimum of this. So when the absorb mass at V is T, then we just say that the sink is saturated. And the excess is just amount of flow at V, which is not absorbed. Right? So, for example, here, if the sink is 10 and there are 20 flow here, then the excess is going to be 10 here. Okay. All right. So observe that really just by definition, like when there is no excess, then it means that this F is a flow, not just pre-flow. When there is no excess, all the mass is absorbed at something already. So F is a flow satisfying source and sink function. So, okay. So what we wanted to make happen is that when you're given source and sink function, then like if you don't do anything, there will be a lot of excess at the source, and you want to find the flow such that there is no excess at any node. So the flow satisfies source sink function if there is no excess. And if you verify the math, like it's gonna work out, but I guess you get the intuition, right? Okay. And okay, and this is just like when we say that F is a pre-flow, then the flow at every node is at least 0, but I already said this. Okay. And here it's kind of repeating things, but I think it's just worth saying because it makes ourselves more familiar with terminology. So if you have any set S, then the initial mass, the total initial mass at S is gonna be equal to these three terms exactly. One is the net, like here is the source S, and you have some initial mass at S. So this mass can either go out of a set or is absorbed inside S, or it is not absorbed yet and it doesn't go out too, so it is an excess at S. Right? So the mass either go out or is absorbed or remain there, not absorbed. So, and that's why you will get this equality. Okay. Makes sense? Okay. And the proof, you can do the math, but yeah, this just explains the idea. Okay, now we can talk about the push-relabel algorithm, the framework, I mean. Okay, so the framework is here. You are always given a graph and source and sink function, but also some parameter h. Okay. It will govern like the height of the label, and I'm gonna tell you now. So what I mean by what is the notion of h here? Like what's the meaning here? So the algorithm, like given this as an input, the algorithm will maintain two things. First, it will maintain a preflow with respect to source and sink function. And the next thing is that it will maintain a vertex level that map each node into a level from 0 to h. Okay. So you think of this level as a height of a node. Like a node will start, like think of initially the preflow here will be like 0 floor, and the height of every node is just all 0. And you will start trying to send flow, and along the way you will need to raise the height of a node when it is necessary.
Does it represent the excess?
The height does not represent the excess. Yeah. So, but yeah, there will be some relationship, but not direct correspondence. Okay. So in picture, and the way I draw it is gonna be like this. Like the vertices here will have height. The highest guy is gonna be on the left, and the lowest guy is gonna be on the right. So like you think of this as maybe as height h to 0. And intuitively, you want to send flow from higher to lower guy. Okay. So this is really just for intuition. Now, the following will capture the property of F and L, the thing that we keep maintaining throughout the algorithm. That is, first, every node here, which is like level is more than 0. Every node here will be fully absorbed. So every node that has level at least 1, the absorbed mass at U is the sink capacity of U. You will always have this. Okay. So I'm describing the invariant of the algorithm first before telling you what is the algorithm. This is gonna be something that always holds.
Now, what was L again? Sorry.
Say it again.
What was L again?
L?
Yeah.
L is it's just a level of the algorithm, the level of vertices that the algorithm will maintain.
Okay.
And now I'm telling you like the property of L that the algorithm will guarantee.
Okay.
So it will be such that any node with level more at least 1, it will be such that the flow will be absorbed. The flow will be fully absorbed at this node. And next thing is that if you look at any edge UV, if U is here and V is here, and if this is like skipping level, like if this is 1 and this is like level 3, like not 2, if the level of U is greater than level of V plus 1, if it skip the level, then the flow will be fully saturated from U to V. So the flow must be such that it's sent from U to V in the saturated way. Okay. if you have seen blocking flow, this is something that is actually like resemble what is actually blocking flow will certify this exactly too, but it doesn't matter if you have seen it. Any question about these two things? So two things, right? Everything above 0 is fully absorbed, and any edge that skip the level in the downward direction must be saturated in this direction. Okay. Okay. And if F and L certify this, I will say that F and L is a valid state. And it will be the case that throughout the algorithm, F and L will be valid. Yeah. And now, the next thing is that at the end, we will also have that we will say that F and L is a valid solution if additionally every node that have level below H will have no access. So every node here have no access at the end. Okay. So this is what we want to make sure, like F and L remain valid all the time, and it is a valid solution at the end. Question?
Then there shouldn't be any nodes in H level, right? In the end.
So if there is some node in H, it means that there is still some guy with like, okay, if you get a feasible flow that satisfies the sourcing demand, then there is no node in H. But if it can actually happen that there is still actually some node in H with access. But so here we kind of allow actually that like sometimes the algorithm does not succeed, and there is some node with access in H. But we will just stop it there. We will not try to send access from guy in H. Yeah.
And still the algorithm is success. So do we say, is it completed or successful?
So
Will satisfying delta comma P or
no. If there is node with on in H and with the access, then it will not satisfy sourcing, right? But it's just the end of the algorithm. Yeah. We will still say that like as long as there is no everything here have no access, we will still say that we allow the algorithm to end with this. Yeah. Okay. And by the way, it's gonna be helpful to think of residual graph too. So residual graph is defined as follows. So for any edge UV, the residual capacity is just defined to be the capacity minus the flow on this edge. So it's kind of say like how much the capacity remains to be sent along this edge. Okay. And the residual graph is just a directed graph where the edges in this graph is just the one with residual capacity more than 0. And you can see that the first invariant, the thing about which says that any edge that skip the level need to be saturated, it just means that in the residual, what it means in the residual graph is here, right? That is any downward edges in the residual graph cannot skip level. Like any guy that go in this direction, it only go one by one level. Okay. So now we can, like, this is the invariant that we want to make sure had happen. Now I'm gonna tell you the algorithm. The algorithm is here. You can start initially by setting F and L to be like all 0. And you see why trivially is this valid. Well, the condition here only talks about the guy that have level at least 1, so it doesn't matter. And the condition here is about the edges that skip the level, but here everything is at the same level at 0, so everything is satisfied. Okay. But so you can always start with this 0, flow, and level. But actually, the algorithm will actually work even if you don't start with the 0, flow, and level. And level, you can actually feed F and L, which is valid, as an input. And at the end, it will return you like a valid solution. If you give any valid state as an input, it will give you valid solution as an output. So in today's class, we will use this thing, the trivial valid thing. But next class, we will actually need to input something which is like non-trivial. Yeah. Like to do some like warm start. Yeah. Okay. And now the algorithm inverse work as follow. So we will say that so there are like a level of nodes, right? Up to 0. And we will say that the vertex is active if it is still in this region, level is less than h, and it has access on it. So know that like the goal of the algorithm is really just to remove access from every node. But we will give up doing that once the level of the node is already at h. Yeah. But as long as the level is not at h yet, if this guy have access more than 0, we look at that node and call it active. And from the active node V or U, we will either push from U or relabel U. This is why the name push-relabel. Whether to push or relabel, it depends. We need to define the following. So we will say that the edge or arc UV in the residual graph is admissible if this is U. So you really just look at level I, and this is I minus 1. You look at all nodes at the lower level, and if there is some node V on the lower level, like strictly like just one level below, such that the residual capacity is still more than 0, you can still send flow along it. Then you call that edge is admissible. So if there is an admissible arc, UV, then you push the flow from U to V. Okay, so we think of L as a height, and we move the flow from higher level to lower level. And actually, why don't we try to look further? Like, why don't we try to look for lower level?
Saturated, right?
Yeah. The reason is that if you assume this invariant that we said before, any edge that skip the level are already saturated. So you cannot actually send flow to those guys anyway. This is why it makes sense to just look at the guy like just one level below only and try to send flow to those guys. Okay. Like the guy that have lower level, residual capacity is going to be 0 by the invariant. So you cannot send to those anyway. Okay. So if there is an admissible, if you can send flow basically to lower level, you send. Otherwise, it means that there is no admissible edges from you to the guy to the next level. So what you will do is that you will relabel the node. And by relabel, I mean to make it higher by one level. And that makes sense, right? Because the excess that we said that you cannot send flow to lower level. So maybe you need to make it higher so that it can be sent to some other guy. Okay. Like, for example, there might be some edge here, and with residual capacity more than 0. But at this point, we don't allow sending yet. But if we make U higher here, now it can send to this guy. All right. Okay. So in pseudocode, it's just here. Like, this is the main algorithm. It's given graph, sourcing, and parameter h. And you actually can give like f and l as an input too. And as long as you need to make sure that f and l is valid. So what it does is just keep looking for active node, the guy with lower level than h and have some excess, and try to push or relabel. And whether to push or to relabel is just you ask if there is an admissible arc from U. If there is, from U to V, just push from U to V. Otherwise, relabel. And by pushing, how much should I push? Here is how much.
Residual.
So you will push as much as the excess that you have, but cap this thing by the residual capacity of the edge. And this thing gonna be more than 0, right? Because U is active, so it has some excess, and UV is admissible, so there is some residual capacity, so it's more than 0. So you actually pushed something. Yeah. So by pushing this much, it just means that the flow along this thing is added by this much. And by the level, it's just to increase the level. Question about the algorithm? Okay. So the intuition is the algorithm keep trying to move excess to sink, but the way this thing can move only move from higher to lower level. But it tried to do this up to some extent. Once some node have level h already, then you stop trying. once you try to raise it to level h, then whatever. Yeah, just. Okay. So now let's analyze it. So what we will show is that the algorithm basically will always transfer valid state to valid solution.
What is H here? Like how is H chosen?
H is going to be the parameter that you can choose. It depends on the application. Like sometimes you set H to be like n plus 1. Sometimes you set it to be 1 over 5. Yeah. So basically when you want to send max flow, you will set H to be like n because you really want to send out the flow. You don't want any excess. But when you try to find just some phi sparse cut, you will set H to be like small, like 1 over 5. That's going to be enough.
So we set H to be the diameter of the graph, so we find the max flow.
That is true, yeah. I think so. One sec. Is that right? It seems to be the case. I need to think about it to verify this.
Okay.
Yeah, it seems so, but yeah. But this is surprising. It shouldn't work somehow actually, because otherwise someone should have claimed that max flow can be solved in m diameter times, and this is not in the literature. So something, yeah. Okay. All right. So okay. So let's try to see why we always like. First, I need to prove to you that the invariant that we said we want to maintain is really maintained. If it is initially valid, F and L is initially valid, it remains valid throughout. And there are just two things to be checked, right? If an edge skips the level in the downward way, then we say that this thing needs to be saturated. So let's assume that it is maintained, and when it can be violated, only this can be violated only when you increase the level of a node, right? When you increase the level of, like, if this is U, and it used to have something like this. Now if you increase the level of U to here, now this edge are the guy that might violated the invariant. But you see that it will not be violated just because
You would have to push the flow
yeah,
if it's there
right,
and make this inactive, right?
yeah. So if it turns out that this guy as a label have residual capacity more than 0, it means that before the level, this guy have residual capacity more than 0, but that is admissible edges, an admissible edge. But if there is an admissible edge, we wouldn't call the level, so that's why it's fine. Next is any guy that have level more than 1, at least 1, it is fully absorbed. So note that when you increase the level from 0 to 1, if you increase the level of U, then U was active, right? That's the only reason we look at U. But when U is active, it means that the excess at U is more than 0. When you have excess, it means that everything is fully absorbed at U. Okay, so at that time, we all U is fully absorbed when you increase the level. But this flow at U, the absorption here never decrease. Why is that?
Because you are always pushing only, right? You never.
Yeah, because when we push the flow out of U, we never push more than its excess, right? That's why once it is fully absorbed, you don't put the thing that already absorbed out of it. Yeah. So then it means that it is fully absorbed throughout. Okay, so this is it means that it remains valid all the time. And so next is the after termination, then this is a valid solution. So the only thing we need to check is that everything here has no excess, right? That's the definition of valid solution. But we stop the algorithm when there is no active guy. When there is no active guy, it just means that there is no one here which is with access. Yeah. Okay. All right. So when you stop, everyone below level H have no access. And it means what? It means that actually, if after termination somehow no one have level H, then it means that all the excess is 0, no excess at all, which means that the flow really satisfies the source and sink. So, right? And the flow is feasible too. Why is that?
We never exceed the capacity.
Yeah, we kind of look at the residual capacity all the time, right? So we respect the residual capacity, so it will respect the capacity of the original graph. Okay. Wow. I'm much slower than I thought, but okay. So now we will analyze the algorithm a bit. Okay. So first note that I will count how many times we call push and how many times we call relabel. Okay. So note that label only increase, never decrease, right? So it means that each node can be relabeled at most h time. So the total number of relabel is nh. Next, let's count the number of push. To do that, we will actually look at two types of push. I will say that a push is saturating if after pushing you saturate the edge. Otherwise, it's non-saturating. Okay. So the saturating push is gonna be smaller, easier to bound. The reason is that suppose that I make a saturated push from U to V, right? Then after that, the residual capacity is 0. If I want to make another push from U to V again, then it means that I must have push in the opposite direction. Otherwise, because I cannot push again, because it is already 0. Okay. But to push from V back to U, it means that the level of V must have increased by at least 2, so that I can move the flow from higher to lower. So this level must have increased by 2 between any consecutive saturating push. So it means that there can be at most H over 2 push from U to V, which is saturating. Now summing over like both direction from V to U and U to V, and over all edges, then you have that the total number of saturating push is like MH. Okay. Next is the unsaturating push. It's going to be a bit harder to bound. Here we will need some potential function. I will define this potential function to be summing over all node with excess. Among this guy with excess, I sum the level of it. Okay. So why this is nice? Like for bounding unsaturating push, because look at each unsaturating push, right? Every time I do this thing gonna be decreased by at least 1. So like if this guy you have excess like 5, and the residual capacity here is like 10. So after I do this unsaturating push, excess at U gonna be 0. This becomes 0, this becomes 5, and the excess here become 5. But basically the excess move from a guy with high level to excess of a guy level below, right? So this sum is just decreased by 1, right? It moved from like level U to level below. Okay, so every time you do unsaturating push, you decrease this. And now I want to say that everything else can increase this potential function, but not by too much. Once I can do this, it will bound the number of unsaturating push. So let's see. How about saturating push? Ease of saturating push can increase this lambda by h minus 1, just because like if let's say if this is like 2, then after moving, then this is going to be 3 and this is going to be 2. So this is just one new guy that with excess. So you just add one more term into the sum, but that can be at most h. But the number of saturating push is mh, so the total is mh squared. How about relabel? Well, each relabel can increase the level by 1, but there are this many relabel, so nh here. And initially, this is going to be small too, just because each node has label at most h. So that already bounds the number of unsaturated push. Okay. So here we have seen push-relabel algorithm, and we have bound the number of basic operation of push and relabel. And to really so you can see that it takes polynomial time for sure. And to really implement things, there is some data structure details that I need to tell you, and we will continue about this